Alright, so welcome back. We're going to continue with implementing your lab. So we're talking about Huffman coding, compression, cool stuff. And we started by implementing the nodes themselves for the Huffman trees. And so all these nodes will appear inside of the Huffman tree that we finally build up. They will be of type HTreeNodePointer, and secretly they will either be one of the subclasses. Okay, it'll either be a leaf node or an internal node. A leaf node holds a character and a frequency. A internal node holds a left and a right pointer and a frequency. Okay, the frequency comes from the HTreeNode class. Its parent class is where that is stored. Okay, so now the idea is we're going to implement the Huffman coding class, which keeps track of the tree. It packages up all of those textbook operations. So let's get started with that. Let's go to the .cpp file now, and the first thing that we're going to do is implement our constructor to actually go and build the tree. Okay, so oh, I'm sorry. Before that even, let's talk about how we're going to use this tree inside of a priority queue. So we're including queue for priority queue, and we're eventually going to want to compare the pointers that we're going to store inside of a priority queue. Okay, eventually we're going to put HTreeNode stars inside a priority queue. So we need to tell the priority queue how to compare. Those pointers. Remember that we want to give priority to the nodes with the smaller frequencies. So we're going to make a custom comparison class to actually go and return true when, remember it's backwards, when P2's frequency is smaller than P1's frequency, okay? Because of the way that less than is used in the priority queue standard library implementation. So we're going to return true when P2's frequency is smaller than P1's frequency. Okay, so that is as simple as saying return whether or not P2's frequency, because we have a getFrequency method, is smaller than P1's getFrequency method. See that? It's beautiful. And we get these because, well, we don't know, thanks to inheritance, we don't know what this HTreeNode is. We know it's definitely not an HTreeNode itself because this is a abstract class because it has a pure virtual method. So it's got to be a leaf node or an internal node, but we know because of inheritance that they all are going to have a getFrequency method. It's going to be the one that they inherit. Okay, that's the idea there. So we have getFrequency already, and now we get to worry about building the actual tree using our constructor. Okay, so let's implement the constructor now. Let's go ahead and go down here. Remember, we're working on the Huffman coding class itself, so we're going to build a constructor just like this. Okay, so we're going to use this IF stream to go and build our thing. Dun dun dun. I don't know why it's currently complaining. Oh, it's probably currently complaining because I need to say Huffman coding : Okay, so we need to build the tree inside of this constructor. That's all we need to do. How in the world are we going to do it? Aha! Okay, so this is how we'll do it. We'll just call build tree using our parameter. Ooh, it's almost as if I was thinking ahead when I was designing this class. Okay, so we'll just call build tree on ourselves. Okay, we built the tree. Beautiful. Now we need to implement the destructor to remove the tree. And so remember that the destructor is going to actually work if we just say delete. All we need to do is say delete on the root of a tree. And we'll successfully delete the entire tree. Isn't that beautiful? So that just means, okay, the one thing that we have that we're going to make on the heap eventually in the Huffman coding class is going to be the root of our tree. This unordered map, it's a standard library thing. It's got its own destructor. It's going to get automatically called, and it's beautiful, and it's going to work perfectly. We need to worry about this because now we're allocating our own memory. So let's worry about that by deleting it. Okay, so all we have to do in our destructor is seriously just delete the root. And this will call, this will correctly delete the entire tree. It's beautiful because of the way that the destructor is recursive. When it needs to be. All right, that's nice. So that's our destructor, and now we're going to implement the build char freak table method, and it's the one from your book. So let's go and look at that. So character frequency table. There it is. So a dictionary for us is going to be hash table. So and we're not taking a string anymore, but we're taking a file itself. So we're going to add to our frequency table. So technically we already have one because the constructor made us our char freak table. So we're going to build it up inside of there. Okay. So let's get working on that. We're going to use an IF stream instead of a string. It's more efficient that way. And yeah, the table is already a member variable, so it's already constructed. We don't need to return it. We just have to add to it. It's remember that it's called char freak table. Okay, just add to char freak table. Okay, so the idea is we're going to go through the entire file, a character at a time. Okay, so how in the world do you do that? You might not remember your IF stream stuff, so let me pull up the documentation quickly. Okay, so here's the IF stream documentation. What you can do to get a single character out of a file is to say get. All right, and you can just keep getting stuff, and eventually it'll actually return itself. It'll return the file itself, so we can just keep on checking. Hey, did our get function work? By calling it and giving it a character as a reference to set. Okay, so that's beautiful. We can just say char c while ifs.get c, and so this will keep iterating. So it'll keep being true, like this entire thing will become true as long as there's still part of the file to read to. Remember the CSCI 40 stuff. And okay, now all we need to do is add to our char frequency table. So we just read C. We just read a character into C. Okay, so as we said, dot get, we use this one to get a single character, just like this one. So it's actually exactly this that we're implementing right now. Okay, let's make this happen. So we're going to get a single character, and we're going to add it to the tree. So it depends on whether or not there's already a character at that index in our hash table. So we need to make sure and see if it's already there. If it's already there, we'll just increment it. Otherwise, we're going to say that we saw this character the first time. Let's set its frequency to be 1. Okay, hopefully that makes sense. So either we've seen the character before, in which case we'll just add to the current table's value of frequency. Otherwise, we'll set it to 1. Okay, so let's see here. So if char_freq table dot count, so if C is already in there, then we're going to say, okay, let's just increment. We'll say char_freq table dot at C plus plus. Okay, so just increment it. Otherwise, we just saw this character for the first time. We just saw C for the first time. Its frequency is currently 1. Okay, so char_freq table dot in place, add C and 1. Okay, so the idea is, again, remember that this frequency table takes characters to their frequency, so chars to ints. Okay, beautiful. So I believe that this will correctly make things work. Let's make sure. Yeah, we're not going to return any tables because we just built one up inside of ourselves, inside of our current object, our Huffman coding object. So that's beautiful. It's all well and good. Now let's work on the build tree method. Scrolling. This one's more interesting. So we're going to use the frequency table and a priority queue. Okay, let's make this happen now. Dun dun dun. Oh, sorry, where is it? Build tree, there it is. Oh wait, did I? Did I make this happen yet? Let's see here. Implement the build tree method. Well, first of all, I need this. And actually, what this needs to do first is remember that this is where our program starts. This is where the constructor happens. So it's going to call build tree to build the tree. And the first thing that we need to do when we build the tree is to actually go and make the frequency table. Okay? That's the idea. So we're first going to build the frequency table by using our build char_freq table to actually go and do that. Okay? So we're going to say build char_freq table ifs. So now we have the table, it's been made. Oh, and sorry, this is Huffman coding, : There we go. So we got the table, it's been made, and now it's our job to do the rest. So nodes equals new priority queue, 4 character frequency and table, add it. So let's do this. We're going to make a priority queue of, now this is where it gets interesting. It's a priority queue of htree node pointers, because every node is going to be a pointer to itself. And because we're using priority queues, and we have a custom comparison, we have some more work to do in the templates. So we need to get all the way to this compare class. That's the 3rd template argument. So we have to go through the container argument, and we'll just use the default one for the type. We'll use vector of htree node star. All right. And then we can give our comparison, which is, remember, compare htree node pointer. That's our priority queue. That's how we do it. Okay? All right. So now we've got that, and the next step for us is to go through every character and frequency in our table and go ahead and push that. So this is another time to start using. We have to iterate through our hash table, right? It's an unordered map. How in the world does one iterate through that? Well, you've seen ways to do it. I guess technically we can look at one of the examples. So you can use many different ways. can use the iterator version. You can most likely also use the range-based for loop version. But sadly, I don't know where the example of that is going to be. Aha, there it is. Here's the range-based one. You can say auto for everybody in the hash table. It's got a first and a second because it's giving you back pairs. Okay, let's actually do it the iterator way. Just be let's be old school. So we have to say begin and end, and we have an iterator that is a pointer to a pair. So it's got, you can think of it that way. So it's got a first and it's got a second, which is the first is going to be the character, and then the second is going to be the int, so the character and its frequency. All right. So let's go back to the implementation now in the book. So for every character and frequency and table, we got to iterate through the frequency table now. So we'll say for, this is gonna be interesting. So it's unordered map. Let's go back to the .h file. You can just use auto here, but we're going to do it very, very carefully. I'm going to spell it out for you. We're taking our time here. For an unordered map iterator, call it IT. It starts at char freq table begin. It ends, we don't want it to go to, it's one past the end, char freq table dot end IT++ or plus IT. So that's how we iterate. And now IT is the char, IT second is the freq. Okay. So we'll say this is going to be called character and frequency in the pseudocode from the book. So we'll say char character equals IT first, and int frequency equals IT second. Beautiful. And then we're just going to push a new leaf node into the queue, just like that. I guess they call it nodes, so let's say nodes. Why not? Nodes.push. Now we're going to push a new leaf node on the heap. So how do we do that? We're going to call its constructor. Leaf node with a frequency and a character. Hey, we have those. Cool. Push a new leaf node with a frequency and a character. It's all coming together now, isn't it? So now we have a giant priority queue with a bunch of leaves at the moment. And now we're going to go through this loop and continuously pop stuff off. All right, so while our priority queue has more than one thing in it, so we're going to have to do size, okay, priority queue dot size. It's the number of elements in the priority queue. Let's go back here. So while nodes.size is greater than 1, here's what we'll do. We're going to pop the two lowest priority nodes. So left and right are nodes.pop. So now remember what we're getting out. We're getting out H-tree node stars. So and pop won't quite work because C++ is not the same as this ADT in the book. So we have to use top, right? Pop is not actually going to give anything back because it's void, but we can use top and then pop. Okay? That's the idea. So we will do just that, top and then pop. So it's not pop, it's top, then it's pop. Okay. Oh, I have to give a name for this thing. It's called left. The first thing that we're going to get out is left. So we're going to get out left, and then we're going to get out right by popping. It's the new top. Then we're going to pop that, so that's all gone. And then we're going to push the combination of those nodes. All right, so this is a min heap after all. The new frequency, freq sum apparently, is the frequency of both nodes. They could either be leaves or internal nodes. We don't know what we're building up. We just know that they're H-tree node stars. But they always have frequency. Equals left get frequency plus right get frequency. And then we will give the new node that stores them both. It's going to be the parent of left and right. So I guess in the book we're calling it parent. It's going to be a brand new internal node with the new frequency and the left and right children. Okay? So, dun dun dun. Internal node star parent equals new internal node with the frequency sum, and then the left and the right, so left, right. And that is the constructor call to internal node, which itself is an H-tree node, and it takes the frequency of the left and the right and sets them. All right, so now if we are ever given an internal node, we can call, like, hey, get left and get right to actually get those things, because we overrode those default silly implementations from the base class. All right, so that's beautiful. Very, very nice. Back to the code. Frequency sum left and right. Very nice. We now have an internal node star, and we're going to push that. We're going to push it. Nodes.push parent. Oops. Whee. And it has no problem doing that. Remember, it has no problem at all doing that, because parent is an internal node star, but nodes, it takes H-tree node stars only, but that's okay. It can treat an internal node as an H-tree node. It doesn't matter, right? Because it's a subclass. So it's happy with that. And now, we are essentially almost done. Now, eventually, we're going to pop out of this while loop, which it's getting kind of long. So that's the while loop right there. Oh, and oops, I think I didn't close the original for loop properly. That's where it should close. I think I have one too many of these now. Sorry about that. Good thing I caught my error. We want to make the entire frequency table first. Oh wait, I think... Yeah, we want to make the entire leaf nodes first. Okay, so now all the leaf nodes are made. And so then we're going to use everybody that we put inside of our nodes loop. Sorry if you caught that error before me or you were confused. The while loop goes outside just like in the book. Left, right, push the parent. And so now, once this while loop stops, we've got just one big tree. We can get that out. So we're not going to return nodes.pop. We're going to actually set. We need to go and set our tree root. Okay? We set our tree root to that node. So tree root equals nodes.top. Okay, that's all. That's all we needed our priority queue for. Now we're done with it. It can be destructed as this method returns. Okay, so that is a very long explanation of the build tree method. Hopefully that makes sense. We're just making everybody a leaf to start. Then we're using our custom order in the priority queue. So we're using so many different data structures to do stuff very quickly. Okay, it's very nice. It's very easy to get the min thing out of a priority queue. Super, super nice to do that. Okay. All right, now let's implement the GetCodes method, which is again just following the book. So, how in the world is this going to do? How in the world is this going to work? It's going to call getNodes recursive with the correct starting values. And then we're also going to implement the getCodes recursive method. So let's actually implement this one first. Let's implement getCodes recursive first. Whee. So it's no. So now we're going to say, all right, so we're given a node, a prefix, and an output. So node, prefix, and an output. So what we're going to do is, the idea is we're building up inside of output a map that we can iterate through in order, because it's an ordered map. Going from characters to their Huffman codes, okay? Capital H. All right, so that's that. And let's see here. GetCodes recursive. I'm going to do all that stuff. Now we're ready. So node prefix output. If the node's a leaf, we're going to be like, oh yes, we got to a leaf. We know exactly what the output for that node is because it's got a character and it's got the prefix that we've been building up. If you remember me talking through all of like, the prefixes now, once we get to a leaf, we've built it up. Okay, so we're going to say, if the node's a leaf, what do you know? We have a way to discern whether or not a node's a leaf, don't we? If node is leaf, which we have implemented properly, it's always going to be false unless it's actually a leaf, because an internal node, it gets the parent's implementation is leaf is actually a leaf for leaf nodes. Otherwise, in the other subclass, it's going to be false. Isn't that nice? It's all coming together. Inheritance is super. All right. If it's a leaf, we are ready. We have an output. Output node, output the character with a prefix. Okay? So output dot in place node get character and prefix. So we've built up the prefix so far recursively. Else, we need to recursively get the stuff. And you know what? Can I just copy this? More or less. So really this is going to be GetCodes recursive. And this is not Unicode. It's an arrow. Oops. And it's not left or right, it's get left and get right. And the prefix is we're adding 0 and 1, and then also keeping our output along for the ride, because we're just always building up in our output because it's a reference to a map. All right? Whee. Oh, and I forgot semicolons, because there are no semicolons in the book with pseudocode. So this is a void function. It's not actually returning anything. We're building up the output map right there. Okay. That is the idea. So I think we're set there. Now we just need to implement the actual getCodes method that's going to wrap around this recursive function in just a prettier way for the user. Let's see. Where are we there? What does it look like? This one right here. So it's actually going to return a map to the user. So let's make the map that we're going to return. Just call it ret for a map. And then we're going to call our getRecursive method with the correct starting values, which are these right here. Give it the root, give it an empty tree, and give it our blank map. Okay, so we're going to say GetCodes recursive, give it the tree root, give it the starting prefix, which is empty because we don't know where we've gone yet. We haven't made any decisions whether or not we've gone left or right. And then we say our output. So, and then finally, we're giving back this thing, so I'm going to return this returnable map. Okay, it'll get returned. Beautiful. And that is GetCodes. Isn't that nice? Calls GetCodes recursive. And then finally, we're going to implement the compress method. And that'll be that. So what compress does is actually use this. It uses all this stuff. It uses the codes that we built up. It uses the original file, and it goes through the file again, and it goes and changes every character into its code, okay? And compresses it that way. And, I mean, technically it's giving back a string of bits, but who cares? Okay, so, So really these ones and zeros take more space to encode, but you know what we're doing still. Okay, so that's the compress method. Let's see, does not match any declaration. Oh, I'm sorry, not HTree node, but Huffman coding. And it's got to return a string. Okay, so the very first thing you need to do is go back through the file now. So use the codes to go through the original file in IFS and extract the codes. All right, so maybe this is the one thing I'm going to make you do yourself. So you're going to start a string. The first thing that you need to do is go back to the beginning of the file because we've already read from it. So we need to go back to the beginning of the file using these two lines. Okay, so now we're at the beginning of the file. So now you need to read each character from the file again. And use and translate each character using the codes map. It's the parameter up here. Okay, we've been given this. In main is where I call this. Okay, I have made the codes up here, we've compressed them, and so I give them back. Okay, that's the idea. So let's see. Yeah, and so this is the Huffman compress function from your book. And this one I think is easy enough for you to do yourself. So I'm going to pause, implement this so I can show you the final answer. But I'm not going to show you this code. And again, remember that I'm not giving you any of this code that I've written in class. That would be too easy. So I'll be right back. All right, so now I think we have everything. And I want to go to the lab instructions, just briefly. There's not going to be a lab intro video anymore because there's no need. But I have made a makefile, and we can compile our stuff with make compress, and hopefully it's going to work. So here's the compress.cpp file. And so we can compile with make compress. Here's the makefile. And then I've also made a run compress tests thing. Technically, you could have just said make run compress tests because it would have made compress anyway. And what you can do is run that to see what it does. All right, you can get some output out of that. Let's go back to here. So you can say, hey, it actually compiled. You can say make /compress. Is just going to fail because we didn't give it enough command line arguments. So we can say make run compress tests to actually go and run things. And here is what we got back. Okay, and I have saved a special file that is the expected output for this. So here's my AutoGraders implementation. Hopefully it should be very, very similar. This is what we should see when we run all this stuff. Okay, and we'll talk about it after we confirm that it's working. Let me show you how to do that. So the way that you can save the output of the run compress test, you can say make run compress tests, and then you have to do a very fancy operator that says, okay, there's standard error output. I want you to redirect that to standard output. Don't worry too much about this. You can ask me about it in office hours, though. I'd be happy to explain. It goes along with, you know, that there's C in and C out. There's also C error. Okay, there's something along those lines that you may have heard about. And then you can redirect that now to a file called like myoutput.txt. So we can say, run this, redirect the, I think it's that, yeah. Redirect the standard error to standard out, and then take everything, take the standard output now, and create a file called, I guess it's myoutput. So now it ran it, didn't show you anything because it put it all in the file. You can say vim myoutput to see what it was. So here's all the stuff, and hopefully it was all the same. So we can say, you can say diff the expected output and my output. And oh man, if it gives you nothing, that means there is no difference. If there was a difference, you could be like diff, I don't know, expected output and the make file, where there are different things. Then it would tell you like, okay, on the left side was the answer, like this is the difference, and then on the right side, these are like little arrows telling you what the difference is. Okay, that's the idea. So we did it right, and so now let's inspect this expected output. So what it did was it ran /compress on Shakespeare, and there's a lot of stuff going on in Shakespeare here. There's a lot of lines being formatted with spaces and things. Here are the second sonnet and things like that. Where's the cool one? Isn't it like 16? That's the one everybody knows. No. It's sonnet 18. That's the one everybody knows. Okay. Cool. What's happening is, okay, we're extracting, like we're building the tree, we're running it through, like we're getting the frequency table for every single character that exists in the entire works of Shakespeare. And it turns out that the most common characters are the ones that are going to have the smallest like codes, and it looks like 01 was space itself. Okay, see that? It was just space. So there's a lot more spaces than a lot of other things. And here is like other punctuation, like single quotes, things like that. Periods. Numbers aren't that common. Semicolons are more common than colons, apparently. Capital A, it gets one less bit because it's more common than capital B. You see that? E as well. Yeah, that's the idea of quotes. Lowercase, this is where the action lies. It looks like the E's are a whole lot more common than the A's because the E's end up with taking up only 4 bits, whereas A's take up 5 bits. And then the O's also take up 4 bits. And we could play around with this all day. So it looks like T happens a lot too. Maybe he says like the, thou a whole lot. Super fun, right? And so then it's going to do the same thing. And then also it'll test the compress. So hopefully you implemented that correctly. And that is essentially your lab. I think we did it in time. You still have that one thing to implement. I didn't give you the entire answer, but I gave you most of it. And I hope that you see now how like all these pieces that we've been talking about in class fit together. This is your last lab. Okay? This is a culmination of everything that we've done. All the object-oriented programming, we talked about inheritance most recently, and then all the data structures that we're using to like efficiently do all this stuff. Okay? Building frequency tables, we're building the tree using priority queues, we're like taking advantage of all this stuff, of all of these data structures that do what we want quickly. So with that, let's briefly talk about the running time complexity of this entire thing, of building the tree, let's say. So assume that the input is n characters long, so you know immediately that it's going to take O of n to build the frequency table. Because, now, remember that, where is that? It's using hash tables, which take constant time, and it's going to iterate through the entire thing, the entire file, which is n times, and this, I'm claiming, is constant work. Okay? It's constant because you can go inside of the table very quickly. It's constant time. Okay, so that's O of n to build the frequency table. Then we need to worry about, okay, what's happening when the tree's getting built. So, the idea is, well, we're at most ever going to have n nodes, technically, because every character could be different if you wanted. At most n nodes in the priority queue. That's fine. How long does it take to push them all into a priority queue? Because we need to worry about this one now. It's constant to make this, then we need to add the time that it takes to push them. Well, that's going to average out to be n log n, right? Because we're doing a log n operation, insertion into a heap. We're doing that n times, okay? And then, while the nodes.length is greater than 1, we're going to iterate this while loop. The while loop is going to iterate, let's see here, the number of characters technically minus 1 times, because every time we're going to add, like, we're going to combine two things, right? N minus 1 times. While loop iterates n minus 1 times, and what is it doing inside of those n minus 1 iterations? Well, it's doing heap operations. It's popping the priority queue, and we're also inspecting the top as well in our implementation. So this is log n time to do that, okay? And making nodes, adding things, pushing is again log n. These are constant. So inside of the while loop, it's log of n. Because it's doing heap operations. And it's log of n on average. I can be less hand-wavy in office hours if you'd like, but the idea is it's not always log n. Like it goes down and up because, well, once you pop this queue enough times, it's going to have less than n nodes in it, so it's not going to be log n anymore. It might be log n minus 1. But on the average, you even it all out, it becomes log n. All right, so that's the reason it's doing heap, because it's doing heap operations. So technically, it's n log n in total. But actually, there are at most 256 different characters. So really, it's no longer n in some places. It's at most 256 nodes in the priority queue. It's at, therefore, it's, let's see here, 256 log 256 after you've built the frequency table. That's constant. What? While loop iterates 255 times. What? While loop's body is log n on average. It's not log n, it's going to be doing at most 255 iterations of not log n, log 256 work. That's again constant. What? So really, n log n in total, well, if you have more than 256 characters, suddenly the size of the char type matters. And it's not n log n anymore. It's the while loop in total, it's going to be miraculously, let's see here, 255, which is a constant, times constant work. So that means, like, put all this together. Therefore, the actual work was done in building the frequency table. It was O of n instead of n log n. So it really depends on your analysis. Depends on how many characters you can really have at most. Because if there's a constant amount, suddenly a lot of these things, it was n log n, but what was n? 256. So that's a beautiful analysis to end this lecture. All right, so the last thing that I want to talk about is just some quick exercises, which I think would be helpful if you wanted to further understand this stuff. Actually output a file, like the binary version of a file. The zeros and ones are the int, like are the numbers. Like output binary, please. Actually compress a file into a smaller file. That would be nice. And then also, decompression is something that we didn't talk about in this lab, so get that working. Like decompress from like our string output or your actually compressed file back into the original file. Like make sure that that goes both ways. Okay, it's its own inverse. That's the idea. And with that, hopefully that was a fun last lab. I'll give you a little while to implement this. It'll be due after Thanksgiving, and yeah, you shouldn't have any trouble getting it all working and turning it in for full credit. So that is my Thanksgiving gift to you. I think that is everything that I wanted to say, unless I got something wrong, and I'll come back in an edit. But that's what I want to say, and I will talk to you later.